Okay, so let's continue. Welcome back to EE210B. Okay, so I will be talking now about complex gradient vectors. This is part of the background material that I mentioned last time. Okay. Remember, the course consists of 5 parts. The first part is background material. Some of you may already be familiar with it, others may not. So this is your chance to catch up, or at least to get the notation and the formulation consistent among all of us. Okay. So what I'm going to do now is introduce the concept of complex gradients. You all know how to differentiate a function f of x relative to a real argument x, where x is a scalar. Here I'm interested in introducing the concept of differentiating a function relative to a vector, and where that vector can be complex valued as well. So why do I also deal with complex valued vectors? It's because in many applications in signal processing and communications, it's not uncommon for you to have situations where the argument is complex valued. Your channel may be complex valued. Your frequency response may be complex valued. For example, in the cognitive radio example that I mentioned before, where you are trying to estimate the spectrum or the frequency response, you may be dealing there with complex valued variables, right? So it's not uncommon for you to encounter situations where the argument is complex valued. Okay, so I need to introduce that extension. Okay, so this presentation is based on this reference, Appendix A, from the text I mentioned to you before. Okay, so all of this information you will find over there. Okay, so let me start. So G of Z interesting. Okay, I get it. So G of Z is my function. G itself is a scalar valued, right? Is a scalar valued, but this argument Z, it can be a scalar or it can be a vector, okay? And it can be real or it can be complex. The case when it is a scalar and real, all of you are familiar with it, right? The more interesting case for us here is when it's a vector and complex, okay? So let's continue. So let's assume that Z is complex. Let's start with that case, which is more general and more interesting for us. So Z is a complex random variable. So I'm going to denote its real part and imaginary part by x and y. So G of Z, you can now view it as a function of x and y, right? So this function of a complex variable Z becomes a function of 2 variables x and y. And I denote the real part u of xy and the imaginary part v of xy. Fine? So far? Okay? Because G of Z itself, even though most of the time G of Z for us would be real valued, because G of Z will be the cost function that we are trying to minimize, so it will be real valued. But in this particular appendix, I'm allowing it to be more general. So G of Z can be complex valued. That's why you have the V component there. Fine? So this is just representation. You can think of G of Z as a function of Z, or you can think of G of Z as a function of X and Y, and we denote the real and imaginary parts separately like that. Okay, very good. Okay. Now, how do we define the derivative of G, right? This is from complex analysis. How do we define the derivative or the complex derivative of G relative to Z? This is the definition, right? This is very similar with a slight technical difference, or actually not slight, but an important technical difference relative to the real case. This is how you define the derivative in the real case, right? You take the difference of G of Z and G at Z plus delta Z, you divide by delta Z and take the limit as delta Z goes to 0, right? You can write it in terms of delta Z going to 0, right? Or you can express that same ratio in terms of the x's and delta x, y and delta y, right? These are 2 equivalent representations. Now, delta z is a complex number, right? So when you are differentiating a function f of x, where x is real relative to x, and when you say delta x is going to 0, that delta x is going to 0 along the x-axis only, right? That's the only direction it can move. In the complex plane, delta z can move to 0 in many different ways, along the x-axis, along the y-axis, or follow some other trajectory within the plane, right? So this is my delta z. It has a real and imaginary part. Let's assume that I make delta z go to 0 in the following manner, along the x direction. I set its imaginary part to 0, and delta x goes to 0. Fine? So if that's the case, and you go back to the definition of the derivative, right? If you go back to this definition here, where delta y now is 0, delta y is not there, but this is going to 0, right? You will find that this definition here, under the limit, becomes the partial derivative of u relative to x and the partial derivative of v relative to x. Fine? You agree with that? Okay? You just come back here, because remember, g is u plus j v, right? And this is also u plus j v. Okay, so you have the real part here minus the real part over delta x. That gives you a partial derivative of the u relative to delta x. And then you will have the partial derivative of the v component relative to delta x. If you put these things together, you get that the complex derivative can be written like this in terms of the partial derivatives relative to the x component. Fine? Now you can do the same thing. I can make delta z go to 0 by making delta x 0 and delta y go to 0, right? Now I make delta z go to 0 along the y-axis. So if you go back to the same definition, you will find that g prime of z, the complex derivative now, is given by this expression, right? So if you compare, before I had the partial derivative of u plus the partial derivative of v relative to x, right? This is now v relative to y, u relative to y. But these are expressions for the same derivative, so they have to agree, right? They have to agree. If this function is to be differentiable at z, in which case we would say it's analytic at z, then this expression has to agree with this expression, which means the partial derivative of v relative to y has to agree with the partial derivative of u relative to x, right? And the same thing here. So these two conditions together constitute what's called the Cauchy-Riemann conditions. Okay, so for the complex derivative to exist, your function has to satisfy these two conditions. Okay, these conditions are sufficient, and you can show. Okay, so you can show they are also necessary. Okay, I mention it here. If the functions u and v are continuous. Okay, they are also. They are necessary. They will also be sufficient if the real and imaginary parts are continuous. Okay, this is a technical detail. It will be satisfied in most of our cases. Okay, that these conditions need to hold for the complex derivative to exist. Fine. Okay, so let's take an example. Okay, remember. Okay, the partial derivative of the real component relative to x, the imaginary component relative to y. Right? And then you switch, right? Okay. So let's take an example. Let's take this function g of z equals the norm of z squared. Is this a real valued function or a complex valued function? A real valued function, right? If z is complex, the norm of z squared, which is z star z, will always be real valued. Very good. If it is real valued, so the function itself will be given by this, x squared plus y squared, right? Where x and y are the components of z. So when the function is real valued, its v component will be 0, right? And it will only have a u component, right? So if you come back here to the Cauchy-Riemann conditions, the v component is 0, so this right-hand side here is always 0, and this right-hand side here is always 0. So for these conditions to hold, you need the left-hand side to be 0, right? So if you differentiate u relative to x or u relative to y, you need both of them to be 0. So if you go here, if you differentiate this relative to x, you get 2x, relative to y, you get 2y. None of them are 0 except at the particular point, right, 0, 0. Right? So you can see, even for this simple case, quadratic cost function, real valued, the conditions do not hold. Right? So this is just an example to show you that the notion of complex differentiation as defined is not the notion that we'll be using for this reason. Because for the functions that we'll be dealing with, right, these functions do not satisfy the Cauchy-Riemann conditions. Okay? Now, that's not a problem for us because what we are interested in, we are not interested in computing the complex derivative of the function. We are interested in finding the points where the function is a minimum or a maximum or a saddle point. Finding the points where finding the stationary points of the function, okay? In the manner I'm going to explain. So, to do that, okay, I'm going to introduce another definition for the derivative, right, based on what's known as the Wirtinger calculus. Okay, this is one name that people use to refer to what I will be talking about. Okay, so come back here, come back to these expressions here to motivate the new expressions I'm going to give you. Here I have an expression for the complex derivative. Here I have another expression for the complex derivative, and they have to be equal, right? Okay, so if I add them and divide by 2, I get an expression for the complex derivative as well, right? Okay, so if I add this plus this and this plus this and divide by 2, what will you get? Okay. Sorry, okay, not add, there is a j. So let me show you the expression. I add, but one of them is multiplied by a j. Okay, here it is. Okay, so you see, this is the first derivative. If you go back, sorry. Let me do it slowly. Take this expression here. Okay. Yeah, okay. So take this expression here. What does this look like? Right? Remember, G is U plus V. Sorry, G is U plus JV, right? So this is like the partial derivative of G relative to X. Okay? Here, if you multiply by J, okay, if you multiply by j, you are going to get up to that j the partial derivative of g relative to y, right? So if you combine these two factors and you divide by 1/2, it's a simple algebra, you can do it. You get this expression here, you see? The partial derivative relative to x, the partial derivative relative to y, if you combine them with that j and divide by 1/2, you should recover the complex derivative. If you perform this combination, I'm going to define that as the partial derivative of g relative to z. Okay? I use the expressions I derived before to motivate this. Okay? To motivate this expression. Okay? Now, I can define the derivative relative to g like this, and I can also define the partial derivative relative to z star. Okay? Relative to z star is x minus jy. You can repeat the same arguments, and you get this expression. Now, why are these expressions useful? Because if I find a point z where this partial derivative is 0, if I'm able to find this particular point z where this partial derivative is 0, that means that you found a point x0, y0 where this is 0 and that's 0. Right? The partial derivative of g relative to x is 0, and the partial derivative of g relative to y is 0. So this point that makes this partial derivative, right, that derivative 0, is a point that corresponds to a stationary point of g. Right? You can get it from here, you can also get it from here. So working with these derivatives is useful for us since our purpose is, will be interested in finding the stationary points of the cost functions, actually the minima of the cost functions, okay? So all you have to do is introduce this derivative, which is defined like this, and find the point where it is 0, and that's good enough for us, okay? Now, let's look at some examples, okay? Remember, you differentiate g relative to x, g relative to y, okay? Before the examples, I have this useful relation. You can combine them together, right? So the derivative relative to z is 1 minus j, 1/2. You can combine them together. And this matrix here is invertible, so I can take it to the other side. I can express this in terms of that rather than this in terms of that, right? So this is just another equivalent way of writing these derivatives, okay? And this is the point I mentioned, that if you find a point z where the derivative I just defined is 0, that point z will correspond to a stationary point of your function. Okay? So let's look at some examples. Okay? Let's look at some examples. Take this function g of z equals z squared. Is this real valued or complex valued? In this particular case, it happens to be complex valued, right? Okay, complex valued. So if you find out what g of xy is, so let's do this slowly, right? Replace z by x plus jy, compute z squared. This is what you are going to get. And now apply the definition to find the derivative relative to z star. You are going to find that the derivative of this relative to z is 2z. Consistent with your intuition from the real case, right? That's why these definitions, the way they were defined, are convenient, because they will help you keep much of your intuition from the real case. And the derivative relative to z star is 0, because there is no z star here, and in the complex case, z and z star are treated differently, right? Now, you can do many other examples. For example, here, magnitude of z squared. What do you expect the derivative relative to z to be? Z squared is z star. You can do the calculations. They are done here, but the derivative will be relative to z, you get z star. Relative to z star, you get z, right? And this is a quadratic function in the complex case, right? Quadratic in z. So what's the derivative relative to z? You're going to get alpha plus gamma z star. Relative to z star, you're going to get beta. This is gamma z star, gamma z, right? Okay, fine. So this is how we are going to differentiate a function of a complex argument relative to z, right? And you can see from these examples that your intuition from the real case extends, at least for these useful examples that we will be using, okay? So let's now take this a step further. A step further, okay? What if I have a vector of arguments? And this will be generally the case for us. It's not just a scalar z, but my function g of z is a function of a vector. Okay? So this z now is a vector, a column vector. So I'm going to define the derivative, okay? Also called the gradient vector or the Jacobian. These are names. I will be using most often gradient vector to refer to this. Okay? So z is a column vector. Z is a column vector. So I'm going to define the gradient relative to a column vector to be a row vector. Okay? For reasons you are going to understand soon. It's not meant to confuse you. It's meant to help you. Okay? Some people define it as a column vector. I define it. I prefer the row vector convention for the reasons you're going to see. And what is that gradient vector? It contains all the partial derivatives. Derivative relative to the first entry of z, second entry, and so forth. Okay? So when z is a column, you get a row. And I'm going to refer to it as the gradient vector. Okay? So that's the notation I will be using for it when g is a function of a vector. Okay? With the inverted delta that you see there. So this is the gradient vector relative to z. Okay? And how do I define the gradient vector relative to z star? Z star is the conjugate of z, right? It contains z1 star, z, okay. Z star, if z is a column, z star will be a row. So I'm differentiating relative to a row, the gradient will be a column, okay? So the gradient in my convention, right, if you differentiate relative to a row, you get a column. If you differentiate relative to a column, you get a row. That's all, okay? Just keep that convention, and it will be the vector of partial derivatives, okay? Now, and again, this is convenient because if you find that particular vector for which the gradient is 0, it will correspond to a stationary point of that function. Okay, the same argument we had in the scalar case. Okay, so this is not difficult to see. Let's see some examples. Okay, so here, A star Z. This is an inner product between two vectors, right? What do you expect the gradient vector relative to Z to be? A star. So Z is a column, A star will be a row, you see? So it's consistent with the convention. And relative to Z star will be 0. Now, if you don't believe me, you can go to the definition, do it slowly, you will get that, okay? What's the gradient of the norm of Z squared relative to Z? Z star, you see? You do get, this is the gradient relative to a column, you get a row. So if you use this convention, the results become consistent with your intuition from the scalar case. Okay, so that's why I keep this convention. Okay, very good. This quadratic case, what's the gradient vector relative to Z? A star plus Z star C, right? You get the idea? So you know now how to differentiate functions relative to complex arguments, right? Okay. Now what happens in the real case? What happens when Z is real? There is a subtle difference when Z is real, okay? Everything I talked about is for the case when Z is complex. Let's see what happens when Z is real. Well, I continue to define the gradient vectors in the same manner. The gradient relative to Z is a row, relative to Z star is a column, in the same manner. And these will be now, these are real. So you don't have partial derivative relative to X, relative to Y. Each one of these, you can compute them directly like you compute, right? Like you learned in real calculus. Fine so far? Okay. And now, right, so now I have the gradient relative to Z and the gradient relative to Z transpose. Z transpose is a row, that becomes a column, okay? And obviously, right, it's not difficult to check, right? If the gradient relative to Z transpose, which is this, right? If you transpose the previous gradient, you get this, right? Okay? Very good. So this is a useful transposition property. So let's do this example now. Without looking at the answer, okay, what's the gradient relative to Z? Now, in the complex case, this would have been Z star, right? You would have said A transpose. But now, you will get A transpose, but you see, because everything is real, Z transpose B is equal to B transpose Z. So you will get a B transpose. You wouldn't get it in the complex case, right? Okay. And here, in the complex case, you had Z star CZ. The gradient relative to Z used to be Z star C, and that's it. But now in the real case, you will get a 2. This is like a Z squared in the scalar case. You'll get a 2. Now, again, if you don't believe me, you can do the calculation. I think I have it on the next slide, right? I just take this term and expand it, right? Just expand the term and compute the derivative relative to Z, right? This is just simple algebra. I believe you can do that calculation. Okay, so it is done in the notes in case you couldn't follow. And you will see that you will get that too. Okay, you will get that too. Okay, fine. So now you learned how to differentiate or compute the gradient of a function g of z relative to z when z is a vector. That's important for us because that will be the general case in this class. And The convention here, if Z is a column, you define it as a row. If Z is a row, you define it as a column. Fine? And in the complex case, you treat Z and Z star differently. Right? If you adopt these conventions, then much of your intuition from the real case extends. Fine? Okay? So there isn't much difficulty here. Okay? Very good. So in the previous case, C was symmetric. That's when you got the 2. Okay? When C is not symmetric, if you go to the argument, I did not show all the argument. Okay? To get that 2, I had to assume C is symmetric. Okay? When C is not symmetric, you don't get 2C, you get C plus C transpose. Okay? Again, this is something very simple for you to check. Okay? Just introduce the individual elements, differentiate relative to the individual elements, collect all the derivatives into a vector, you're going to see you get C plus C transpose multiplying Z. Okay? Very good.